Magnetic flux. In order to produce induced EMF inside a coil C of wire conducted by a sensitive galvanometer G, as shown in figure 14.1a, the galvanometer is used to detect any current induced in the coil. Never the coil is a stationary ball magnet. When the magnet is stationary, the galvanometer slow no current. Now if the magnetic move toward the coil C, the galvanometer will show deflection in one direction. In 1831, English scientist Michael Faraday discovered that when the magnetic flux is neat in a state, the conductor charge and EMF is induced in the conductor. The phenomena is known as electromagnetic induction. The interplay of electric and magnetic force in the basic of electric motors generates in many other modern technologies. Faraday law of induction describes how an electric current induced a magnetic field. The conversely, how to changing magnetic field generates an electric current in the conductor. In this unit, we will study the various aspects of electromagnetic induction. Describe how step up and step down transformer can be used to ensure efficient transfer of supplying electricity along cables. Identify the relationship between the ratio of the number of turns in the primary and secondary coils, the ratio of primary and secondary voltage. Explain the production of bank EMF and electric motors. Describe the construction of a transformer and explain how it works. Identify the relationship between the ratio of number of turns in the primary and secondary coil, the ratio of primary to secondary voltage. Explain the production of EV current and identify their magnetic field heating effects. Explain the need of limitation iron covers in electric motors, generators, and transformers. Explain what is meant by motional EMF, giving a rod or wire moving through a magnetic field. In a simple way, computer the potential difference occurs at ends. Define mutual inductor M and self-inductor L and their unit Henry. Describe the main component of AC generator and explain how it works. In order to produce induced EMF, consider a coil C of a wire connected to the sensitive galvanometer G, as shown in figure. The galvanometer is used to detect any current induced in the coil. Near the coil in a stationary ball magnet. When the magnet is stationary, the galvanometer show no current. Now if the magnetic move toward the coil C, the galvanometer will slow how to show the reflection in the one direction. If the magnet is moved, if the magnet is moved away from the coil, the galvanometer again shows deflection but in the present direction. Furthermore, if the magnetic is held steady and the coil of wire is moved toward or away from the magnetic, against an EMF is induced in the current flow. If the magnetic is field stationary inside the coil, through the flux is linking the coil, there is a changing in flux, and hence no EMF is induced in the coil. Therefore, the galvanometers show zero deflection. If the magnetic is moved faster, a greater deflection is observed. In each case, an EMF is induced in the circuit when the magnetic flux through the circuit changes with time. It does not matter whether the magnet of the coil moves. It is therefore relative motion that counts. The basic requirements of electromagnetic induction in the change of flux linking the conductor or coil. A similar effect can be produced by using the apparatus. We call this coil the primary coil. The corresponding circuit is primary circuit induced EMF, which shown in the figure of 13.4. Induced EMF is also may be charged by the particular way of any magnetic flux. So we cannot have the that property of the magnetic is held stationary inside the coil through the flux. A similar effect can be produced by using the apparatus shown in figure. The primary coil, the corresponding circle, the primary circuit, a second coil called the secondary coil, and the right is connected to the ammeter. The corresponding circle is called secondary circuit.